Welcome to the second video in the series for preparation for the TEAS test. In this video, I want to cover the concepts of measurement in the sciences and the use of scientific notation. First, there are two types of, we mentioned in the first video, observations that lead to an experiment in the scientific method. And there are two types of observations that can be categorized for this experimentation or for whatever sparks question. One is qualitative. The other is quantitative. The qualitative, and you can get a lot of information from the words. Qualitative simply describes a quality, like a color or a comparison of two things in terms of just general size or general appearance, whatever. It's very non-specific. Quantitative refers to quantity. That is a measurement. You have to have a number associated with it. And that's where we're going today. We're going to the quantitative side. When we make a measurement in the sciences, we have two components. We have a number, and we have a unit of measure called the scalar. So, for instance, we have examples here. 20 grams. Grams is the unit of measure, right? It's a unit of mass, a very small unit of mass. And 20 says that we have 20 of those units. Units of measure don't have to be single values like grams. They can be compound values like joules second. Notice we have joule and then a dot and second. That dot is like a multiplier. Right? These types of measurements are usually the result of calculations, but they are just as valid. In order for scientists to communicate with one another, we have to agree upon what we mean by each of the units that are being proposed. So there was a system set up in the actually early 19th century called the International System, and proposed several fundamental units that were fixed in value, and everything else will be derived from those. International System is SI units. SI because it's derived from the French word, and the French always talk backwards. So SI units for mass would be kilogram. Something that, and we have a standard kilogram of mass. It's made out of an alloy of platinum and iridium, very resistant to corrosion. And even then, we take this standard mass and we put it in a bell jar with argon gas. And then we put that bell jar in another bell jar with argon gas. Because once the standard is set, if it's corroded, then our standard's no good anymore. So we have to guard it very carefully. And it's kept under constant climate conditions of humidity and temperature. Used to be in a cave in France. I'm not sure if they still do that. But this kilogram is the standard unit of mass. The standard unit of length is the meter. And the meter was based upon the distance between the North Pole and the equator for a longitude that runs directly through the prime meridian. It is the prime meridian. It runs through the observatory at Greenwich, England. And they took that distance and then subdivided it into a manageable size, 1 meter. And then they constructed several bars out of this alloy and protected them as well in argon atmosphere. So you would, if you wanted to standardize your meter, you sent it to the international, the ones who are custodians of the standards, and they would compare yours to theirs and tell you how long yours actually was or how much yours actually, the mass you had. The meter now can be duplicated with a very expensive machine that simply counts the number of wavelengths in a laser light of a given frequency. Time is the second. That's the standard, and it's derived from astronomical units. This is grandfathered in from ancient times. We just standardized what the second means, and we have what's called, you've heard of atomic clocks. We use the radioactive decay of a certain isotope, and our electronics are fast enough to count the decays, and that's what the standard is based upon. Standard for temperature is the Kelvin. Now, the Kelvin, don't be surprised or put off by the Kelvin. The Kelvin is simply a modification of the degrees Celsius, which is used all over the world. Right? Everything is measured in Celsius, except for in the United States, where we tend toward Fahrenheit. But the Kelvin is simply a modification of the Celsius. The ampere is a unit of electrical current, and it's based upon the measure of 1 coulomb of charge that passes a certain point in a conductor every second. And we don't have time to go into the details there, but that's what it means. The amount of a substance is the mole. The mole is, the word is derived from molecule or molecular. It's simply a number of things. It could be a number of molecules, a number of atoms, a number of ions. We could expand it to be a number of chickens if we wanted to. But the mole is so many 6.022 times 10 to the 23rd somethings. It's a huge number. And we're going to find out that it needs to be a huge number because we're trying to quantify atoms or molecules, right? And they're very small. It takes a lot of them to be measurable. So that's where the mole comes in. The candela is one that I rarely ever encounter in chemistry, but it's a measure of luminosity. Those are the fundamental units. Now, if say the meter is too small, like if I tried to measure the distance between Beckley to Charleston, it would be in the neighborhood of 55 or 60 miles. Then in meters, it would be thousands of meters, right? That would be an unwieldy number. So sometimes we want to modify the unit with a prefix. Well, if the meter is the standard, then if I create a new standard, a new unit of measure called the kilometer, that's 1,000 meters, because kilo, excuse me, kilo means 1,000 times. Right here, 1,000. So when we modify the unit of measure, if we say 1,000 meters equals 1 kilometer, right? The distance we're measuring is exactly the same. We're just using a different unit of measure. So, and one other thing you'll notice is when the unit of measure gets bigger, a kilometer is a lot bigger than a meter, then the number gets smaller. And that always happens. And these are various prefixes. Kilo is most often used. Sometimes those of you who are familiar with computer memories, and the byte is a measure of memory. Kilobyte used to be a huge value many years ago. Then megabyte became the standard. And then we had memories that was in terms of gigabytes. And now we have hard drives that will store terabytes of information. So each one of those has a meaning. Kilo means 1,000 times. Hecto means 100 times. Deca means 10 times. Mega means a million times. And notice that these prefixes, they're case sensitive. So if you say this, right, that is a million meters. Okay. Well, on the next page, we're going to go the other direction. If you have very small numbers, we can use a reduced size of our measurement. And notice there's a prefix little m. A little m, if you get them confused and put a capital M in there, and you meant to put a little m, milli is 1,000th of 10 to the minus 3 times, whereas mega is 10 to the 6th times. So if you make a mistake in the case of your m, you could be signifying a radically different measurement size. If we have a measurement that's really small, and of course in the realm of atomic sizes, we're talking nanometers and picometers, right? 10 to the minus 9th or a billionth of. And micro is in the range of cellular sizes under the microscope. So those are your prefixes. Most often you'll encounter nano, micro, milli, maybe centimeter. So a centimeter would be 100th of a meter. So if it's meters this long, the centimeter is only that big. And as the unit gets smaller, the number gets bigger. Okay. That's one way to accommodate the need for different size measurements and how to manage very large numbers or very small numbers. Another way to do it is with exponential notation. Now, most textbooks will confuse exponential notation with scientific notation. Exponential notation, all that's required is in the decimal system, we store up information from the number in powers of 10. So for example, here we have 300. That would be 3.00 times 10 squared. That just means that we've gone 1, 2, right? Ones, tens. Actually, from here to here is tens. From here to here is hundreds. So if we move 2 places to the left, we're moving our decimal from here to here. Now the number is that times some power of 10. The number of places you move the decimal is stored in a power of 10. If we move to the left, we're making this part of the number smaller. This is called the coefficient. Make the coefficient smaller, we have to store up large values in the power of 10. If we go the other direction, say we have this, then we can go 1, 2, 3. And that is 10 to the minus 3. because now the coefficient is that, and 10 to the minus 3 is storing up small numbers. We're going from 0.003 to 3. So we have to store up information in the negative sense. Now, exponential notation doesn't matter what your coefficient looks like. Exponential could be this: 30 times 10 to the first power. That's exponential. Scientific notation is a special case where the coefficient must be between 1 and 10. Okay. All right. So we've made our quantitative observation, a measurement. It has a number and it has a unit of measure. Here's an example, and I'm going long, so I've got to speed this up. 93 million, right? If we're just looking at the number, right, this could be the distance between the Earth and the Sun, 93 million miles. But for the number itself, if we store up all these zeros, we move the decimal to the left 7 places. And now we have a number coefficient between 1 and 10, that's good. And the power of 10 is 7. Okay? All right. If the coefficient ends up as 10, then you got to move the decimal one more time. Because it can't be 10, it's got to be between 1 and 10. Okay. The number of places moved determines what the power of 10 is. If it moves to the left in your number, then you're storing up positive values. If it moves to the right in your number, then it stores up negative numbers. Okay. I'm going to have to skip over these pretty quick. Yeah. Okay, for example, this would be moving the decimal to the left, so we store up powers of 10, 3 places, 10 to the third, 7.882 times 10 to the third. If we move it to the right here, 1, 2, 3, 4, 1, 2, 3, 4, 5 places to the right, negative value of 5, 4.96 times 10 to the minus 5. Okay, so in a subsequent video, I hope to discuss how to calculate things with these numbers, but for now, that's all we're going to talk about.